Quantum mechanics has a bit of a reputation for being incredibly counterintuitive and also mathematically very challenging. I can't argue with the counterintuitive part. As we'll discuss in a minute, the way tiny things like electrons behave is undeniably strange compared to our everyday experience. But I think the second part about the math being super complicated is a little bit unfair. And by the end of this video, I hope you'll agree that the basic mathematical object of quantum mechanics, the wave function, is actually fairly simple. But let's back up a step. When you start out studying physics, you learn about the motion of things like baseballs and pendulums and even planets. All that falls into the category of classical mechanics. And our basic job in classical mechanics is to figure out the position of a particle as a function of time. Or in other words, its trajectory, x of t. About 100 years ago, though, people discovered that the physics of tiny objects, like atoms and protons and electrons, is very different. They're instead described by quantum mechanics. And quantum mechanical particles hardly behave at all the same as classical objects like baseballs. For example, we'll discover in a few minutes that a particle like an electron doesn't follow a single well-defined trajectory when it travels between 2 points. Instead, it's described by a wave function, psi, which is a function that's spread out through space and which tells us the probability of where we'd find the particle when we go to measure it. We'll see in this video how that language of wave functions comes about by investigating a very simple setup called the double-slit experiment. You might have heard about it before. It's pretty famous as physics experiments go. The idea is basically to throw different things at a wall with two little holes cut into it and see what comes out on the other side. What we find will depend on whether we were throwing classical particles, classical waves, or quantum particles. And what we'll discover is that the quantum case exhibits a sort of mixture of the properties of classical particles and waves. That's what textbooks sometimes give the fancy name wave-particle duality. But we'll see how the consequences of this experiment lead us to the idea of the wave function. And like I said, the math that's involved won't be too complicated. Going into this video, the most advanced math you'll need is really just to know a bit about complex numbers. What's challenging is the conceptual idea of describing a quantum particle by this abstract function psi, when again, in classical mechanics, we'd simply write down its trajectory. You might wonder if there's a different way of approaching quantum mechanics that still describes things in terms of regular old particle trajectories, as opposed to this more abstract language of wave functions. In fact, there is. It's called the path integral formulation of quantum mechanics, and it was invented by Richard Feynman, whom I quoted at the start of the video, a couple of decades after Schrödinger and friends first worked out the wave function approach. The catch is, instead of following a single trajectory like in classical mechanics, a quantum particle does a kind of statistical average of every trajectory it could conceivably take between 2 points. But more on that later. This video is actually the first of a series of lessons I want to share with you, explaining Feynman's way of looking at quantum mechanics, because it can give you an incredibly powerful intuition for understanding the way physics works at microscopic scales. And you can subscribe if you want to make sure you see those follow-up videos. For now, though, we need to start with the basics and uncover how all this weirdness with probabilities and wave-particle duality comes about when we study the behavior of really tiny things. So here again is the setup of the double-slit experiment. We take this solid wall and cut two little holes or slits in it. We're going to chuck different things at the wall and see what comes out on the other side. And believe it or not, this simple setup is going to motivate where the idea of the wave function comes from. Let's start with classical particles. So we're going to forget all about quantum mechanics and just suppose that we shoot something like BB gun pellets at the wall. A lot of the pellets will hit the wall and bounce backwards, but some of them will get through one hole or the other. Let's keep track of where they end up by putting a backstop behind the barrier. It's made of clay or something, so that when the pellets hit it, they get stuck. And that way, we can count how many hit and where. If we only have the left hole open and the right one is closed up, and we make a histogram recording where each of the pellets hits the backstop, we'd expect to get a distribution that looks something like this, with most of the pellets hitting in the region behind the left hole. Likewise, if we close up the left hole and only open up the right one, we'd see something like this, with the pellets clustered on the right. And of course, when we open up both holes, the total distribution will look like the sum of those two individual distributions, because each pellet either goes through one hole or the other. There's nothing mysterious going on here so far. We're just talking about the regular old classical motion of these little pellets. But now let's suppose that instead of firing BBs at the wall, we send in waves instead. For example, say we shine a laser beam at the barrier, with the holes resized appropriately, of course. We're still in the realm of classical physics here, but this is a more interesting problem now, because the waves coming out of the two holes will interfere with one another and produce what's called an interference or diffraction pattern on the back screen. And really, these could be any kind of waves, by the way. You could even think about water waves rippling on the surface of a pond. On the other hand, it might actually be harder to try to picture things in 3D, so I'll mainly stick to this 2D picture using the laser light example. If we close up the right hole again, and look at the intensity of the outgoing light on this observation screen, the shape will look fairly similar to what we drew a second ago for the BB pellets. And correspondingly, when you look at the screen, you'll see a band of light with that profile. Let's call that I1, the intensity of the light with only hole 1 open. Likewise, if we close up that hole and open up the other one, we'll get a similar pattern I2 that's shifted over slightly behind hole number 2. There are two key differences here compared to the BB pellets, though. First, there's the obvious difference. The BBs were discrete particles. Each of them hit the backstop as individual lumps. The laser light, by contrast, is a wave, classically anyway. It's a continuous distribution of energy and momentum. The second key difference comes when we open both holes. If light behaved like the BB pellets, we could just add together the two curves here to find the total intensity we should get with both holes open. If that were true, the image on the back wall would look something like this, with a wide band of light. But that's not what you'll see when you shine a laser beam on a pair of narrow slits. Instead, you'll see an image like this, with many little fringes of light separated by intervals of near total darkness. And that's what we call an interference pattern. The corresponding intensity curve with both holes open would look something like this, with many alternating peaks and valleys corresponding to the bright and dark spots on the screen. Clearly, it's not simply the sum of the intensities I1 and I2 that we had when the individual holes were open. We call it an interference pattern because it arises from the two waves emanating from the holes interfering with one another. The bright spots appear where the waves interfere constructively, which just means that they've added together to make a bigger wave. And the dark spots are where the interference is destructive, and the two waves have canceled each other out. The physics going on here is absolutely fascinating. Think about it. With just one hole open, there was plenty of brightness all throughout the middle of the screen, like at this point, for example. But by opening up a second hole in the barrier and letting more light through, a spot like this that was bright now winds up darker than it was when only one hole was open. It's kind of mind-bending, and we haven't even gotten to the quantum mechanics yet. Indeed, the reason we're talking about all this right now is that we're about to see a very similar interference phenomenon in quantum mechanics that's closely tied to the idea of the quantum wave function. And so, before we get there, it's important that we take a couple of minutes to understand how the interference pattern comes about for classical waves. To keep things simple, we'll suppose that the gaps in the barrier are very narrow. That way, after the incoming plane wave strikes the barrier, it breaks up into two spherical waves, psi1 and psi2. Then, those spherical waves travel along until we intercept them far away on this observation screen. But crucially, because the holes in the barrier are separated a little bit apart, the profiles of those two outgoing waves will be slightly offset from each other. The total wave is the sum of the two contributions. Where the two pieces have the same sign, like right here in the middle, they add together constructively and make a bigger wave. On the other hand, when they have opposite signs, the waves cancel each other out destructively. And that's the basic origin of the bright and dark spots we observe on the screen. But let's try to actually make that precise with some equations. We can write the incoming wave as some amplitude a times the cosine of an angle phi, where phi is a function of the vertical coordinate y and the time t, given by 2 pi over lambda times y minus vt. This is the standard sort of form for a wave that's traveling along in the y direction at speed v. If we draw it at a fixed instant in time, lambda is telling us how far apart the successive peaks are, and a tells us how tall they are. In the case of light, those would correspond to the color and brightness of the laser. Of course, a light wave is actually built up of electric and magnetic fields, which are vectors, but it's enough to think about a simple scalar wave like this to illustrate the origin of the interference pattern. And actually, if you've studied waves at all before, You might know that it can quickly become a bit of a pain to write things in terms of cosines like this. It's much more convenient to write down a complex wave, e to the I times phi. The idea here is that we're using Euler's identity, which says that e to the I times something is equal to the cosine of the thing plus I times the sine of the thing. And so we can think of our original cosine wave as the real part of this complex wave. But exponentials like this are much more convenient to work with than cosines. So this is a useful trick for dealing with classical waves. And it'll be essential when we go to write down the quantum mechanical wave function in a minute. Meanwhile, on the opposite side of the barrier, we can write the outgoing waves in a similar way. But because those are spherical waves, they don't just vary with the vertical coordinate y anymore, but instead with the radial distance from each hole. So if we write r1 for the distance from the first hole, then psi1 will be proportional to a times e to the I phi of r1 and t. And likewise, we'll put r2 for the distance from the second hole, so that that corresponding wave is e to the I times phi of r2. The total outgoing wave is given by the sum of those two contributions. Finally, the thing we're actually looking for is the intensity of the outgoing wave, which is what tells us how much energy is hitting the observation screen on average. That should be a real number, of course, so we'll need to take the absolute value of our complex wave. And in fact, the intensity is given by the square of the absolute value. I'll show you how to compute that in the notes that I wrote up to go along with this video. You can get those for free at the link down in the description, and I go into more detail there about a lot of what we're learning here. The algebra isn't too important right now, though. The point is, when we plug in our two spherical waves, we obtain the intensity curve that describes the interference pattern of alternating bright and dark fringes. So the main thing I want you to take away from all this is, again, that we obtained the total intensity by adding together the complex phases emanating from each hole, and then taking the modulus of that squared. One last thing about these classical waves before we switch to the quantum case. There were two terms in the sum here because we assumed that each hole in the barrier was really tiny, so that one spherical wave emerged from each. In reality, of course, the gaps will have some finite width to them, and that's what's responsible for the more intricate interference pattern I showed you a minute ago. But we can also understand the interference for wider slits, or for any shaped gap in the barrier, using essentially the same strategy as we've done here. Because whatever shape you want to punch out of the wall, we can build it up by starting with a solid barrier and drilling out lots of little holes like we've been talking about here. Then each little hole is a source for a spherical wave that propagates outward toward the detector. And to understand the interference pattern, all we need to do is add up the complex phases from all those individual waves. The slick part of the argument is that eventually we'll have drilled out so many little holes that that whole region of the barrier has disappeared entirely and left us with the shape we wanted. That's the idea behind what's called Huygens principle. And we'll come back to a very similar argument in the next video when we talk about Feynman's path integral approach to quantum mechanics. But okay, that gives us enough of an idea of how things work with classical waves. Now it's time to see how all this connects to quantum mechanics, which is where things are going to start to get a little strange, to say the least. Let's run this experiment with the double slit one last time now, but this time by shooting tiny quantum mechanical particles at the barrier, like electrons. Quantum particles are hard to draw, of course, so to be clear, these bouncing balls I'm showing here are just a cartoon. And indeed, we're about to discover that quantum particles don't actually behave like bouncing balls at all. With only one hole open at a time, the story is similar to what we saw before. The distribution looks something like this, with a big bump in the region behind the hole. And moreover, we find that the electrons hit the detector in distinct lumps of energy and momentum. That much is similar to the BB gun pellets. And likewise, if we close that hole and open the other one, we'll get a similar distribution. Where things start to get weird is when we open both holes at once. If our everyday experience with pellets or baseballs or the cartoon bouncing balls I'm drawing here is our guide, we would expect that each particle either makes it through one hole or the other. And so the two distributions would simply add together and produce an overall curve like this. In other words, when you look at the backstop, you'd see the imprint of lots and lots of particles right around the middle and dropping off smoothly to either side from there. But that's not what happens. When we fire electrons at the barrier with both holes open, the spots where they hit the backstop look like this. There are dense fringes where many electrons hit, separated by gaps where relatively few hit. It's another interference pattern, and the corresponding distribution is the same sort of oscillating curve we drew earlier. This behavior is utterly baffling. Think about this region of the observation screen, for example. With just one hole open in the barrier, plenty of electrons will make it through and hit right around there. Now, when we go and reopen up the second hole, you would think that that would simply let more electrons through the barrier, and therefore we'd find at least as many, if not more, particles hitting that same spot. But no, by opening up a second hole and letting more particles through, we find that almost no electrons hit that spot on the observation screen. It becomes a dead zone at the bottom of an interference pattern that we would have expected for waves emanating from these two holes. But the electrons are not classical waves either, because again, they always hit the detector in discrete individual lumps, not at all like a continuous wave. This is completely at odds with our classical intuition about how particle-like objects should behave. And so we'll start to try to come up with classical mechanisms to explain what's going on. For example, you might wonder if the many electrons passing through the apparatus are colliding with one another. And it's those collisions that somehow conspire to produce this intricate interference pattern. But that won't cut it, because we can turn down the power of our electron gun so that just one particle at a time is fired at the barrier. And yet, if we wait a while and record where all those isolated particles wind up hitting the detector, we'll see that over time, they build up the same distribution of fringes, matching the interference pattern we got for waves emanating from both slits. Evidently, each electron is somehow probing both slits at once and interfering with itself. In particular, an electron does not have a well-defined trajectory in the sense we're familiar with from classical mechanics. If it did, an electron that's en route to hole number 1 and happens to be headed for one of these interference dead spots shouldn't give a hoot whether hole number 2 is open or not. But it does, because again, when only one hole is open, lots of particles will hit right around this spot, whereas next to none will arrive there when both holes are open. The fact that a quantum particle doesn't follow a well-defined trajectory means that we can't say for certain where the particle will wind up hitting the detector, even if we know everything there is to know about how the particle was fired at the barrier. All we can predict is the probability of where we'll find the particle, according to the shape of this distribution. We've learned two key things then from the double-slit experiment. Number one, electrons behave like particles in the sense we're accustomed to, insofar as they always hit the detector in discrete individual lumps. But number two, an electron can also behave like a wave in that it exhibits interference. And by the way, the same actually goes for our laser beam experiment as well. If we turn the intensity of the light way down, we'll find that what looked like a continuous light wave hitting our detector was actually a stream of individual particles called photons. And if we send one photon through at a time, we'll once again build up the same interference pattern. The fact that a quantum particle can exhibit both of these sorts of properties, sometimes like what we classically think of as a particle, and sometimes like a classical wave, is what that fancy term wave-particle duality refers to. But the fact is, an electron is not a classical particle or a classical wave. It's a quantum particle, which is something quite distinct of its own. And however counterintuitive it might seem to us humans, who live out our daily lives interacting with the world at much larger scales, there's really no reason to expect a quantum particle to behave the same way as a baseball. So, we've seen now how the double-slit experiment leads us to the idea of wave-particle duality, however unfamiliar it might feel. But given that this is the way the world works, how do we, as physicists, describe what's going on mathematically? Well, like I promised at the beginning, the math that's involved with this experiment is really very simple given everything we've talked about so far. In light of the interference pattern, we introduce a new quantity for each particle that we fire at the barrier, called its wave function, psi. Then just like we had for classical waves, after the incoming wave function strikes the barrier, it diffracts, and two spherical waves emerge from the holes on the opposite side. The total outgoing wave is their sum. And just like before, the modulus of that total wave, squared, takes the shape of this interference curve. That's the wave side of wave-particle duality. But again, the thing we actually observe with our detector is always a localized lump on the backstop. And that's where the particle side comes in. What this interference curve is telling us in this case is not the intensity or brightness of some laser. It's the probability of where we'll find the particle when it hits the backstop. And after we've fired many, many quantum particles at the barrier, we therefore find that the spots where they end up are distributed according to that probability curve. And by measuring the separation between the peaks, we can determine the wavelength lambda of that original quantum wave function we sent in. It's called the de Broglie wavelength. And if we fired off particles with momentum p, it's given by 2 pi times h bar over p, where h bar is a number called Planck's constant, which is the fundamental physical constant of quantum mechanics. So, in summary, each quantum particle is described by a wave function. And the modulus squared of that quantity tells us the probability of where we'll find the particle when we go to measure its position. That's how the wave function formulation explains the distribution of particles we observe on the backstop of the double-slit experiment. Like I mentioned at the beginning, though, there's another way of looking at all this that lets us describe things in terms of regular old particle trajectories instead of wave functions. As we've already seen, though, the catch is that the particle doesn't follow any single trajectory anymore. We have to consider paths that pass through each hole in order to understand the interference pattern that we observe. But now, if we push that further by drilling even more holes in the barrier, we're led to the idea that we actually need to consider every possible path that the particle could follow on its way across the gap. That's our first inkling of Feynman's path integral formulation of quantum mechanics, which, by the way, is also the most direct way of understanding how all this quantum weirdness connects back to what we observe day to day up here in the classical world. But we'll take up that topic in the next video. Make sure you're subscribed to the channel if you want to see that when it comes out. Also remember that you can get the notes for free at the link at the top of the description box for when you're ready to dig in deeper. In the meantime, I'll put a link in the description to an earlier video about the relationship between quantum mechanics and the Fourier transform that I think you'll like if you enjoyed this video. And I'll also put links to a couple of classic lectures by Feynman from the 1960s, which were a big inspiration for the approach I took to explaining things in this video. Finally, I want to thank everyone who supports this channel on Patreon for helping to make this video possible. You can join too at the link up in the corner if you want to see more videos like this. Thank you so much for watching, and I'll see you soon with another physics lesson.